We will start from previous class. It's strange, this is not working. 1 second. Okay, let's check this out. Okay. Okay, so we'll continue from last class. If you recall, we went through the tensile test and I briefly discussed about different properties: ultimate tensile strength, proportional limit, yield strength, and fracture strength, and regarding Hooke's law, okay, for ductile materials and brittle materials. Now we will go for compression. In the case of compression, how do materials behave? Generally, for ductile materials, that is generally for ductile materials, the ultimate strength and compression and tension, they are equal. The properties are equal generally. But there are exceptions. For some ductile materials, this is not the case. Ultimate strength and compression and tension can be different, especially if the ductility in the material is approaching that of a brittle material. Okay, so what is ductility? We will define that as well. Ductility could be defined as the strain in fracture. Okay, so it is equivalent to the strain in fracture. So if the strain in fracture is very large, okay, then it is a plastic material. But if you take a brittle material, the strain in fracture is going to be very small and reaching the elastic strain or the proportional limit, strain at the proportional limit. It will approach the strain at the proportional limit. What will approach? The strain at fracture will approach the strain at yield point. If that is the case, then it is going to be a brittle material. Okay, so especially for ductile material, if the strain is coming closer and closer and closer towards the yield point, then you may have a condition where the ultimate strength and compression will be different from the ultimate strength and tension. For brittle materials, always the ultimate strength and compression and tension are different. Compressive properties are different from the tensile properties. Okay, so if we were to draw in tension and compression, so let's take a note. This is section 1. Lecture. What is the lecture? To be lecture 6. So here we are going to see, again, if this is not active in my iPad, just 1 second. Okay. So now it's okay. So if you take a brittle material and look at the stress strain diagram, Let's say this is the positive stress, positive strain. And then we have the negative strain and the negative stress. Sorry, this should be stress and strain. I made it opposite. Should be stress, strain. Okay. So if this is the case, we have generally for compressive materials, this is what you are going to observe. Then fracture. On compression, you are going to see much larger values like this. Okay, fracture here. So in compression, you will have different properties. In tension, you have different properties for, especially for brittle materials and those some ductile materials as well. In tension, you had cup and cone fracture for ductile materials. For brittle materials, you will have with a straight edge. Okay, so if you see the fracture, especially in tension, the fracture will be with a straight edge. While you go for compression, what happens? Yes, what you are going to see is probably some bulging effect like this, and then fracture. Okay. Okay, so what about torsion? We can also do torsion tests. And in the torsion test, you are going to get torque versus twist diagram. There you can use strain sensors, strain gauges to measure twists and then draw the torque versus twist diagram. From torque versus twist diagram, you should be able to calculate what are the shear stresses. How do we calculate shear stress? We can calculate shear stress by using the formula torque times the radial distance. So radial distance, I'm going to write it as R over J, where J is the polar moment of inertia. So we can convert applied torques into shear stresses, and there will be shear strain. Shear strain can be calculated from I think the formula should be phi over L. 1 second. Okay. So let's write this clearly as the radial distance R. Should not be confused with the gamma symbol, which is the strain. So rather I will put it as R. Okay. Okay. So shear strain is calculated from the twist value, and let's say the twist is phi. Phi over L. 1 second. I recall P over J should be equal to G Phi over L. Okay. So if this is the case, okay. So based on this, the strain, shear strain, should be measured by phi over L. So this is how, based on the twist, we will get what is the shear stress versus shear strain diagram. How does the shear strain diagram look like? It will look very similar to your normal stress strain diagram. You will have an yield point, then reaches a maximum value, and then fracture. Okay, so in this case, in the initial part, we will get what is the shear modulus. Based upon the shear modulus, we can write the Hooke's law for shear stress. So we can write tau is equal to, let us say, G times gamma. Based upon this relationship, we can come up with a form of strain equation. Okay. Okay. So the strain here should be 5 times maybe radius r could also appear here. Okay. There is another property which is called as the modulus of resilience. What is modulus of resilience? In the stress strain diagram, we have the area underneath the elastic part of the curve. Okay, so within the elastic part of the curve, this is the elastic part. Before the yield point, we can call it elastic region. And between the fracture point and the yield point, it is called as the plastic region. So the area of the stress strain curve under the elastic region is called as the modulus of resilience. What does it give you? It gives you what is the energy absorbed per unit volume without undergoing permanent deformation. So it gives you an idea how much energy can be absorbed by the material under quasi-static loading. So this is not under impact conditions, but rather under very slow loading rates, how much energy the material can absorb, that is given by the area under this curve. Okay. So if you were to measure the modulus of resilience, how do we measure it? By taking the area under this curve, half into base into height. So we can approximately take this height to be the yield strength. Okay, so half times Sy times the base length here will be equal to the yield strain value. Okay, so approximately this is equal to this value here. We can use the Hooke's law within the yield point. Let's assume up till the yield point the Hooke's law is valid. We can replace the strain, yield strain, by yield stress over E value, and then approximately write the modulus of resilience as this. But if you look at the units here, Sy has the unit corresponding to it, pascals, which is equal to Newton per meter square. And if you take the strain unit, strain is dimensionless. Okay, so what is the unit of this product? It's still Pascal, Newton per meter square. But here, modulus of resilience has the unit of energy. UR is supposed to have the unit of energy, but energy per unit volume. So are both these units equivalent? We can simply check by multiplying by meter. In the numerator, I multiply by meter. Denominator, I divide by meter, and I get meter cube. What is Newton meter? It's nothing but joules per meter cube. So we have consistent units on the left and the right hand side. So this is the energy absorbed by the material per unit volume. Okay. Where do we use this? In one of the situations where, for example, if you have, assume you have vibration absorbing pads. In some of the machines, you may have rubber pads, some kind of a pad. Okay, not necessarily rubber pads. It looks like a disc. So this is the front view. That's the eraser. So the disc might look like this, with a hole here. Okay. So these kind of pads can be used wherever you can put them. For example, if you have bolted a machine to a foundation, you can put these pads, vibration absorbing pads, in those locations, and we can use this modulus of resilience property to evaluate how much this pad will be able, how much energy it will be able to absorb. Okay, so based upon how much energy it will be able to absorb, we can decide on the dimensions, what kind of dimensions you want. For example, what is the diameter phi you want, what is the thickness you want, etc. You can fix it based upon the modulus of resilience of the material. Toughness is the total energy the material can absorb before undergoing fracture. So this total energy per unit volume is given by the area under the stress strain curve up till fracture. Okay, so again, this modulus of toughness property can be also used in similar situation like these pads. Okay, now again, we have to realize, suppose if you have some other padding material which is absorbing the energy under the impact conditions. In those cases, we cannot use modulus of toughness or the modulus of resilience because it is under impact conditions, and these energies are under quasi-static loading process. That is very slow rate of loading, not high rate of loading as in impact conditions. Example of impact conditions. In bridges, you might have seen big columns, and these columns, if you carefully observe, you will see some kind of a padding around them, especially around the base. Why these paddings are given? In fact, some vehicle, if it comes and hits, for example, at a very high velocity, you don't want the column to break. Rather, this padding will absorb all the energy of the vehicle and it will protect the column. So this is under impact conditions, and under impact conditions, you cannot use these guys. It will be wrong to use these guys. Okay. All right. So how do we calculate the area under the curve? Usually we will have some approximate relationships in the plastic zone between the stress and the strain. So these kind of relationships are just like your Hooke's law. They are generally called as constitutive relationship, constitutive equations. So Hooke's law is one example of constitutive equation where sigma is equal to E times strain, elastic limit within proportional limit, right? But beyond the yield point, sigma may be a function of strain. So for example, there is one power law, simple relationship here. Again, you may have a relationship like this, A epsilon power n. Okay, so under the plastic part, you may have multiple relationships for different regions, and then using these mathematical relationships, you can integrate and figure out what is the area under the curve. Okay, so we have already discussed what is the unit, joules per meter cube in SI units and English units given here. Carefully read this. Measures the energy absorbing characteristics of the material. Unit is this. Assumes low strain rate. Right. So what do we mean? Quasi-static loading. Slow loading rates. Okay. However, for higher strain rates, we cannot use these properties. We have to use impact methods, and we will see what are impact methods as well later. Cold working. What is cold working? What is what does the process do? Cold working increases the yield strength of the material. Okay, yield strength of the material. by plastically deforming the material below recrystallization temperature. Can one of you tell me what is recrystallization temperature? Can anybody explain to me what is recrystallization?
The crystals change shape.
What do we mean by crystals? What is a crystal?
Like
What are we
BCC
talking
and FCC.
Okay, BCC structure, okay. But what is recrystallization? What does it mean? Then does it mean that from BCC it becomes to FCC? What does it mean? So if I say I'm working below recrystallization temperature of steel, what does it mean? So here it means, yes.
It means reforming of the metallic bond.
Reforming of metallic bonds. No, not actually that. So how, by just by applying mechanical forces or something, you think, or so this is about temperature, right? So are we melting it? Are you saying that recrystallization temperature is melting temperature of the solid?
No, doctor.
So it cannot be something about bond. When does a bond break? When you melt it,
Yes.
right?
Look, doctor,
So
it's
what
like
is happening?
when you
Hmm.
increase the temperature and then when you cold it very fast, you're trapping the electrons or something like that. And you change the structure of the material.
Oh, what do you mean by structure? So it is not about BCC, FCC. When you cool down any steel, it forms into FCC structure. If you cool down still below, it forms BCC structure. For example, in the case of steel. So where is the recrystallization temperature? At room temperature, what is the structure of steel? Steel at room temperature. Does it have BCC or FCC? If you recall, BCC. Okay. Now, when we are talking about recrystallization temperature, when we talk about structure, what we are actually talking about is the microstructure. What is microstructure? Microstructure, if you look at the surface of any material under a microscope, you are going to see grains. What are grains? Again, if you recall, these grains, they refer to the orientation or specific orientation of the BCC structure. Let us take it as BCC structure within the material in the case of steel. So in one grain, the orientation of this BCC structure may be like this. In neighboring grain, it can be different direction. Why do we have these different directions in each grain? Because when solidification takes place for the material, several points, suppose if you have liquid, okay, liquid material, okay, as I cool down, what will happen? Inside a crucible, you have liquid material. As I cool the material down, what happens is at various points solidification will take place. And the BCC structure will start to grow in different directions. So here it will grow in this direction, maybe. Okay. And here it will grow in this direction. Slowly, the grain size will increase. Here it will grow in different direction and the grain size will increase. And similarly, so when solidification takes place, there are different points where solidification occurs. The size of the grains, they grow, and when they grow, the direction in which the structure grows will be all different. And finally, they meet at certain points, and these points, they become the grain boundaries. Okay, so this is how grains are formed and based upon different directions of the BCC structure in which it has solidified. When I say recrystallization, if we increase the temperature to a certain limit, not to the melting point, much below melting point, at one point again these grains, they start to reform, and that temperature, the minimum temperature under which these grains, they start to reform, is called as recrystallization temperature. They melt away, grains, they melt away, again they start solidifying when you cool below recrystallization temperature. Okay, so when we say change in structure, the grain size and other properties of the grains, they start to change, and therefore we say there is a change in structure. So we are making sure we are much below recrystallization temperature when we do the cold working process. And what do? We apply the mechanical force on the material beyond the yield point, and let us say at a point I remove the load. What will happen? The material will go down here, causing causing certain recovery of elastic strain to a certain amount, but there will be a permanent plastic strain. Now, if you reload the material after completely unloading the material, if you reload the material again, initially the yield point was here, now the yield point has moved to a new location. The material has higher yield strength than before, and this is achieved through the cold working process. So cold working increases the yield strength of the material, and we do not apply any heat, only mechanical loads beyond the yield strength, load it and then release it. So why do we do this cold working? Sometimes this is a very cheap method to increase the strength of the material for your particular application. Maybe the raw material which you have has lower yield strength than required for your particular application, and you want to increase the yield strength, and this is how you will increase. Okay, is it clear? So this is cold working process. Okay. Okay, so before we move on, we discuss further properties. Suppose I load it again and I want to increase it further. I can keep on increasing the yield strength of the material. Here I can go all the way. The maximum value will be ultimate strength value at necking. But as you reach closer and closer to the fracture point, although you increase the yield strength of the material, the ductility of the material goes on decreasing. Why it goes on increasing? What is ductility? We have defined it as the strain at fracture. Where is the strain at fracture here? Here. But once I do a cold working process, see, initially the strain at fracture is this whole length. Okay. Now, after I do the cold working process, now my initial point has shifted to this point here, point A. And point A is the 0 point, new 0 point now. Now, for my particular material, the new strain at fracture has to be measured from the point A, and therefore Now my epsilon f becomes this particular length. So the ductility of the material keeps on decreasing as I do more and more cold working. And if I keep on continuing with that, finally, when it reaches a point here, it will become a brittle material. Okay, so there is a limitation here. And we have seen before that advanced high strength steels overcome this limitation of cold working process by applying some other manufacturing techniques, which includes heat treatment, which includes cold working, mechanical processes, and also includes adding additional elements within the material, causing precipitation of certain certain materials within the microstructure of the steel. Thereby, it will increase directly. What we have seen here is ductility reduces as yield strength increases. If ductility reduces, then the ability of the material to absorb impact loads also decreases. But in the sophisticated manufacturing processes, not only the yield strength increases, even the fracture toughness also increases for the material. Okay, fracture toughness or ductility also increases. Okay. Now let's go to a property which is called hardness of the material. What is hardness? Can any of you define what is hardness? Have you guys heard of this term?
The strength of the material to a localized pressure.
Localized deformation. Okay, so strength of the material to resist localized deformation. Okay, that's a good definition. Or let's say we can rather writing it as strength, because strength is a well-defined property for a material. Rather, we should say here in this case, ability of a material to resist local plastic deformation. So this is the general definition. Okay, general definition that is given. When I ask you what is the definition of stress, how will you give the definition of stress? How is stress defined? Anybody?
Force applied to a certain area.
Right. So I can write a formula. When I say stress, internal force over area of cross section. What is the formula for hardness? Define hardness, because when I say as engineers, we need to come up with a formula using which we should be able to calculate some value. Then that particular quantity like stress is defined. What is the formula for hardness? General formula for hardness. Have you seen any formula for hardness?
Yeah, we have one. We have table, and there was formulas for each test for hardness.
But is when I calculate stress, I have let's say how to put it. Okay. When I say mathematical definition of stress, okay, when I ask you for mathematical definition of stress, what would be the mathematical definition of stress strictly? I'm not sure if you guys have taken solid mechanics with me and whether stress was mathematically defined this way. When somebody asks you what is the mathematical definition of stress at a point, remember stress is defined at a point mathematically. So we will discuss in third chapter in detail about this, but generally this is how we define. Okay, in terms of limits, limit delta A tends to 0, delta F over delta A. This is the mathematical definition of stress. Okay, now the general definition of stress, depending upon the type of load we apply, slightly different, maybe F over A. If you remember from solid mechanics, you had other formulas for bending stress, M over I times Y, and we also had another definition based upon torque. Okay, so these are some formulas which we have derived for calculating average stresses based upon a fundamental formula for stress. This is the fundamental formula for stress. This formula doesn't change whether you apply bending moment, torque, or axial load, whether you have combination of these loads, whatever may be the case. This is the mathematical formula, exact mathematical formula for stress. It could be normal stress, shear stress, only the force will be normal or shear force here. But the formula is same. So the stress quantity is well defined. It is a single formula. Have you seen such a single mathematical formula for hardness? Again, stress is well defined with a single formula. No matter what test I do, if I want to mathematically calculate stress at a point, this is the formula I will use. It doesn't matter whether it is torsion test, it is tensile test, compression test, whatever test you do, bending test. Have you seen such a well-defined formula for hardness?
No, because hardness is not well defined.
Yes, so that is the answer. Hardness is not a well-defined property. In fact, there is no formula for hardness like stress here. We can use some theory and derive these formulas. If you go for hardness, what is the theory? Have you seen any theory? No theory also. No theory behind hardness. What do we have? Just like layman definition. That is all we have. What is the layman definition? Ability of a material to resist local plastic deformation. What the hell does it mean? How do I calculate anything out of this? Nothing. It means nothing. Okay. So what the hell is hardness finally? We really do not know what we are measuring. We do not know what we are doing. Okay. But somehow we have a feel of what this property of hardness is, just a feel. Okay, and what do we do in Rockwell test? We have different shapes of tools which go and penetrate the surface of a material locally, and when it penetrates with the different loads, in each case we apply different loads. In Rockwell, Brenell, Vickers, who decides what is the amount of load I should apply? Based on what? Nothing. So we have some experiments we do, but we do not know what we are measuring, why we are applying certain force, why the tool bit used for penetrating a particular material has a particular shape. None of these we don't know. We just use these experiments to come up with some numbers based upon some empirical formulas. Okay, now when I say empirical formulas, they are not based upon any theory, rather just based on observation. empirical. Empirical means the term empirical means observations. Okay, so just merely based upon observations, we come up with some value based upon some formulas we used in Rockwell, A, B, different formulas, empirical formulas. We calculate it and give a number. So what are these numbers? These numbers can be treated as relative scales. For example, if you go and ask a customer to rate a product on a 1 to 10 point scale, subjective, right? It is very subjective idea. So each guy will rate whatever he feels. In the same way, these experiments, they give you some numbers based upon some empirical formulas, like subjective ideas. Okay, and what we can do with these relative numbers, we can keep it for having certain idea about relative properties of the materials. Okay, so why do we use hardness? It gives you these hardness numbers, which are relative numbers or relative scales. Okay, just like the scales, 1 to 10 point scale. It gives us a certain idea which material can cut another material. It gives us certain idea. Okay, for which material I can use to cut another material. So for example, I can use diamond to cut anything, including glass. It will cut through glass as well, like butter. But if I use a metal steel rod and try to cut glass, it's not going to cut it, because the hardness, that relative number, is not that high in comparison to glass. So this is one practical application of these hardness values. There is also another practical application. There is a way to empirically relate these hardness numbers, these relative numbers, to a property like yield strength. So we can empirically relate them through graphs. And by empirically relating them through graphs, we can get the yield strength and the ultimate strength for steels. And the empirical relation gives this relation based upon, let's say, Brinell hardness number in SI units and English units. For cast iron, another empirical relationship is also given. Again, these are empirical formulas. It's not based upon any theory. These are empirical formulas. What is the use of these formulas? Suppose you are in a field and you want to test whether the imported materials, they are according to the standard. You cannot pick each and every material, go and do in the laboratory tension test, destroy the material and do tension tests. Rather, what you can do is you have an portable testing machines, hardness testing machines. You take them and locally test the property. You take a sample, test the property, what is the hardness of the material, then use these empirical relationships and deduce whether the strength of the material is according to the standard you have. Okay, so that is another use for this hardness properties. Okay, what is the unit of hardness? Generally, since it does not have a theory, no proper theory, assigning it a unit for these hardness numbers have no meaning. Okay, however, for practical situations, whenever I use the formula, inside the formula I can do some calculations based upon some units. For example, If you take the Brindle hardness formula, you may have specific formula, and you may have some force quantity and some numbers here based upon the radius of indentation, some function you might have. Okay, like square root of f of r. In what unit I'm going to substitute r, in what unit I'm going to put f value here. So here we can see the different units, right? So if it is you want in a KPSI, the hardness value HB also has to be calculated appropriately here when I substitute. I can put here R in meters, R in millimeters, F in let's say kilonewtons, newtons. What unit should I use here? So for clear specification on how I calculate HB, I will have units associated with it. Okay, when you are publishing data, you will have units associated with it for this reason. Not that hardness itself has a unit. Okay, did you guys understand what I said? The property hardness does not have a unit. However, for convenience sake, they will put units when they publish the data. Okay, so that is the reason. Okay, so we have seen, now we go for impact properties. Now there are various kinds of impact tests, Charpy test, ISO test. Charpy test is usually done to approximately identify what is the ductile to brittle transition temperature, another property. What is that property? We will discuss in this slide. But before going there, so Charpy test is used for approximate identification of another property. ISO test may actually produce some material property data for impact tests. So in both these tests, what do we do? Approximately this is the case. What we do is we have a specimen. Okay, so try to draw the specimen here with a V notch like this. So we have a specimen with a V notch like this, and what they have is a hammer. Generally, a hammer is tied to a dial, fixed to a dial. Maybe I should draw it near. Dial may have a pointer like this. Okay, and then you have the hammer. The hammer, when released, will go and hit the particular sample. The sample will be fixed on a base here. When the hammer goes and hits the sample, it will break the sample, and then the hammer will rise a little bit away here. So basically, you will have the hammer after breaking it, it will rise here. Okay, so this hammer will come to this position. Now, according to the hammer position here, the dial will also change its location here, and it will give you how much height the hammer has raised. So you have the initial position of the hammer, and therefore you can calculate what is the potential energy of the hammer simply using the formula mgh. After you release the hammer, this potential energy will be converted into kinetic energy, and some of the kinetic energy will be absorbed in breaking this particular sample. After the energy, certain energy is absorbed, the kinetic energy of the hammer here will be reduced, and then it will rise to a certain extent here, showing how much potential energy is lost. You may have also frictional losses here. All this will be calculated, and we can evaluate how much energy is absorbed here. So the final potential energy, initial potential energy, so Pi, forgetting about the frictional losses, we can write the energy absorbed by the material here as P initial minus P final. And if you have any frictional losses, you can also include that. By doing this calculation, we can figure out how much energy is absorbed by the material for fracturing the material of particular size. Now, these kind of experiments are used to come up with a plot, okay, plot for impact cases. Okay, so let's see here. What kind of a plot? For example, a plot like this: energy absorbed by the specimen, okay, at particular temperature. We can do the experiments. How much energy is absorbed at specific temperature, and we can repeat the experiment and come out with a curve like this. For example, steel. In the Charpy test, we come out with this kind of a plot, and what you observe is for a specimen like steel and other materials which have BCC structure in particular, they exhibit a phenomena called ductile to brittle transition temperature. Ductile to brittle transition temperature. Mostly BCC materials. So one of the examples is ferrous alloy steel. And what do we observe? When we reach 0 degrees centigrade, which is identified as the DBTT temperature for steel, the energy absorbed, the ability of the material to absorb energy below sub-zero temperatures reduces. What does it mean? It means at higher temperature, steel behaves like a ductile material. At lower temperature, same steel material behaves as a brittle material. So here we have ductile property. Here we have brittle property. Therefore, it is called ductile to brittle transition temperature. Okay. Now this was not known during your Titanic accident. The guys who designed the ship Titanic, they were not aware of this property. And nobody knew about this property until investigations revealed that at sub-zero temperatures, steel becomes brittle. And this is what happened. The Titanic hull, what is hull? Hull is the portion of the ship here. Water here, this portion is called hull. So it went and hit against the iceberg. It was sub-zero temperature. The material became brittle, cracked, and then failure. The water went inside the ship and sank. So this is one of the reasons for Titanic failure. Okay, so let's see further here. What happens to the properties when we, for example, increase the rate of loading? So at very low loading rates, we can see certain properties. The ultimate strength of the material is this value. As I increase the loading rate, the ultimate strength of the materials initially seem to decrease and then suddenly increases. At very high strain rates, it increases a lot. So what does it tell you? It tells you that if I increase the strain rate of the material, the same material which is ductile in this region behaves more and more like brittle material. Okay. it becomes stronger. What about elongation? You can see this will clearly show you that the material becomes more and more brittle. So 1 second. This is yield strength, and we can see here total elongation. Okay, so as I increase the loading rate, the elongation seem to increase and then reach a constant value, which shows that it is more like a brittle material. The elongation does not increase. The yield strength also seem to increase very rapidly, more and more like a brittle material. Okay, so this is how this is the effect of increasing the loading rates. Now the previous experiment, what we have seen, in that experiment we increase the load very slowly, probably within this range, and did the experiment. But if we increase the load at a faster rate, you are going to see that the properties will be, stress strain graph will be completely different for the same material. Okay. So the understanding of these things is necessary. You should know what is the limitation of properties you are using. So we already went through this. Temperature effects. What happens to properties under quasi-static loading when I increase the temperature? The material will become softer and softer. Okay, and this is important to understand creep properties. So we will discuss about creep. Let's take about a 10-minute break now, and we will come back and discuss about creep later at 9:10. Okay, so we will meet again at 9:10. Did you guys hear me? We will meet back at 9:10 a.m. Okay, we take a 10-minute break.
Okay.
All right, we will continue now. So we just talked about in the previous slide the temperature effects, and we were talking about creep. What is creep? Creep is the continuous deformation of the material under constant load for a long period of time at elevated temperatures. So at high temperatures, when you apply a load, constant load, even a constant load, and over long periods of time, what happens is there is strain. Okay, there will be strain, continuous strain over long period of time. One example you can see is that if you are able to visit very old buildings, centuries old, and if you look at the glass, any glass window, you will observe that the thickness of the glass in the bottom of the window will be greater than the thickness of the window on the top. What has happened? So under constant gravity, what happened is glass flows. Although it appears to be solid, glass is actually flowing over several years. And you will see that it flows down and becomes thicker in the bottom while it is thinner on the top. This is called as creep phenomena, and such creep phenomena we observe in applications, especially which is at elevated temperatures. So what do we mean by elevated temperatures? For example, if you take the aircraft propeller and power plants, what is an aircraft propeller? You might have seen under the wings of the airplane. Okay, you will see this big turbines attached to it. So this is the example of creep here. There is an example of creep here. These turbine blades, they are exposed to temperature of 650 degrees centigrade over periods of time under constant loads or maybe variable loads. So where the loads come from hot gases flowing around it. Okay, continuously flowing around it, and these blades, propeller blades, will be subjected to this load at very high temperatures and for hours together. And what happens is the phenomenon of creep. Under such loads, continuous deformation takes place, and at one moment fracture will occur. Okay, so there are three stages under which creep takes place. Initially, the strain of the material is very high. Strain rate of the material is very high. So on the y-axis, you can see here deformation or strain and time. So initially, the rate of deformation is very high. You can see the slope is high. Slope is very high. Then after it passes the first stage, it goes to the second stage where the slope reduces and the rate of deformation is constant. This is a straight line, approximated as a straight line. And then again, the tertiary stage, the rate increases rapidly, the rate of deformation, and then fracture. Okay. So in the first stage, you have elastic and plastic deformation. Initially rate is high, but the rate of deformation decreases because of the strain hardening phenomenon. In the second stage, when the strain hardening phenomena has reached to a maximum limit, the rate of deformation is almost constant. Okay, and it is constant because there are more dislocations produced as well as some kind of annealing effect taking place. So what is annealing? You know, when you heat the material, what happens? The hardness of the material goes down. So something like that happens here. Although the number of dislocations increase because it has some annealing effect also, it remains constant. The rate of deformation remains constant. During the second stage, life of the specimen is decided. How long the specimen or the member has is decided during the second stage. And in the third stage, if it goes, it leads to high reduction in area, very high strain rate, and then fracture. If it reaches third stage, that's it. The life of the turbine blades, for example, will be finished. So how do we determine the life of a specimen? We model for creep in the second stage. So here, when we say model, here we obtain the relationship between stress and strain rates here. Okay, so I put an epsilon and a dot above. So what does it mean? It is a time derivative. It's a function of strain rate, not just strain. Okay, d epsilon over dt. And based upon these relationships, we will be able to obtain what is the remaining life of the specimen. So this is very important here for material for identifying life of the members. You might have come across cold working process. We just went through cold working process. There is also hot working process where we apply where the material is heated above the recrystallization temperature. Okay, so process in which metal is formed while heating above recrystallization temperature, it is called as hot working process. Refined grain size, that is what you get out of here. Okay, so if you want to get a refined grain size, then you do hot working process. Depending upon the way you cool down, you may have a refined grain size, or maybe you have larger grain sizes. Okay, so the way, depending upon the way you cool, things change. If you have a refined grain size, okay, in a specimen, what will happen? The boundaries between the grains increases, the surface area of the boundaries, and it leads to high strength. Okay, since the boundaries are higher, that means your dislocations and slip phenomena cannot take place that easily, so leads to high strength, hardness, and the material becomes more and more brittle. Okay, but if you want to increase the grain size, then what you do? You heat the material and cool it very, very slowly. Then it will lead to large grain sizes, not refined grain sizes. Leads to rough surface finish. Also, hot working process can lead to rough surface finish. That could be a problem, especially with fatigue life. So some of the processes are rolling, forging, extrusion, pressing, etc. So these are the different cases. Okay. Okay. So when does it lead to again refined grain size? If you give enough time for cooling, then the grains will grow larger and larger. However, if you suddenly cool down, after heating, you do some mechanical working process, deformed, and suddenly cool it down. What happens is there will be many points where solidification begin to take place, and then it also reduces the size of the grains because you do not have enough time for grains to form. Okay. Okay, so in hot working process, you get refined grain sizes. These are some of the sections, cross sections. Then you can couple it with heat treatment process to change the properties again. Okay, so in what way you can change the properties? For example, annealing. In annealing, what we do, we heat above the critical temperature or recrystallization temperature, held there, then slowly cool down. Okay, so this should be think this is completely wrongly stated. I think it may be wrong here. Sorry for this. It should be, I think, instead of refined. So that's what I was also thinking. Maybe in this case, this is wrong. This information is wrong. It's not refined grain size. It should be large grain size. Sorry for that. Hot working process. Usually we cool it slowly in hot working process. So it should lead to large grain sizes. Sorry for that. And then if it leads to large grain sizes, softer the material, more ductile. And this is the reason we do hot working process. So this is wrong. Please make that correction. I will try to change the information here as well. Okay, so again, this should not be refined, and this should be large grain sizes. Okay, large grain structure. When you slowly cool it down, what happens? You have more time for the grains to solidify, and a large grain structure will be formed. It softens the material, increases ductility. When you heat the material above the critical temperature or recrystallization temperature, whatever grain structure you have, that is all erased, and therefore any memory of previous deformations is also erased by this process, and new properties arise according to the large grain structure here. Normalizing is another process which is just partial annealing by adjusting time and temperature. So we do not do a full annealing process, rather a partial annealing process. For some of the cases, normalizing may be required. Quenching, on the other hand, what it does, or the opposite of annealing. In quenching, we take the material, heat it above the recrystallization temperature, and suddenly cool it. When you cool it suddenly by putting the material inside an oil bath or maybe water, what happens? You do not give enough time for heat transfer to take place, but there will be many solidification points where grain structure grows. There is not enough time for the grain structure to grow, and therefore you will have smaller and smaller grain structure. Not only that, if you take steel, you might have gone through this in your materials engineering. You will have more and more hard materials which are formed. Why? The carbon in the steel does not have enough time to migrate from one grain structure to another grain structure, and most of the carbon will be caught in one place, and when the concentration of carbon is high in one place within a grain structure, then martensitic structures or bayonet structures will be formed, and these particular phases of steel have very high hardness, and that leads to high hardness in the material. Pearlite, on the other hand, is soft, but less pearlite is formed in the case of quenching, especially steel, and it leads to hard steels. Okay, increases strength, hardness, but it becomes more brittle. So when you have brittleness by quenching, you may combine it with a process which is called tempering to reduce the brittleness in the material to a certain extent. So that is one way to reduce the hardness. But besides that, tempering has other purposes. What is the purpose? Internal stresses. Reducing any internal stresses. What are these internal stresses? Whenever you cool down a material, it leads to local thermal stresses which are developed. Okay, because Each part of the material expands or contracts differently. You will have internal stresses, and this is not good for materials. To relieve them of internal stresses, you do tempering. But what is tempering? So you do not heat in tempering process above the critical or recrystallization temperature, just below the temperature, and then cool it down. So this way you will be able to relieve all internal stresses. Okay, so this is very important point. Having internal stresses or residual stresses, is also called residual stresses in the material, is not good. Okay, this is no good, and usually this should be removed. So just a comparison between cold working and hot working processes. What does the heat treatment do with respect to different properties? You can see here tensile strength, yield strength, etc. On the x-axis you have different properties from hardness to, sorry, on the y-axis you have different properties from hardness to other strength properties, and also ductility and reduction in area. On the x-axis tempering temperature, especially this has to do with tempering, and what it does you can see here: significant reduction in tensile strength properties, that is increase in ductility, etc. Okay, all right, so let's move on. What does quenching do? Okay, you can see an example for steel and aluminum what quenching does. This is from one of the handbooks, military handbooks. Okay, so this is from one of the military handbooks, and you can see here what is the process that is used: hot rolled, cold drawn material, and you are given a comparison of the properties of carbon steel. This is the, instead of UNS numbering system, we have the ASI numbering system, and you can see here this is a plain carbon steel. So this is a plain carbon steel, and between the hot rolled and cold drawn steel you can see significant variation in the properties of the yield strength. Similarly, the first case has 10% carbon, the second case has 45 1/100th of a percent, sorry, 0.1% carbon, and 0.45% carbon in the second case, 1045. As you increase the carbon content, of course, the yield strength will increase. Okay, and therefore the yield strength is more here. However, for hot rolled it is lesser, and cold drawn you can already see 1045 steel has about 500 megapascal as the yield strength. Again, increase the carbon content, more and more increase. You can see here we do quenching and tempering or tempering operation, and we can see here the tempering temperature is 425 degrees, 650 here. So depending upon tempering temperature, you can see difference in properties. 4340 steel is one of the strongest materials. Okay, highest strength material, and you can see yield strength goes to nearly gigapascals or more. Again, depending upon quenching and tempering operation, you have different properties. This is the effect of heat treatment: significant increase or significant reduction in the yield strength of the material. Again, what is 4340? Molybdenum, chromium, nickel, and molybdenum. Alloying elements are added, and if you recall, the front portion of the skeleton of your car, where you put your windshields, these are made out of these steel materials with very high yield strength properties for safety applications. Aluminum, you have different designations for tempering. For example, whenever you do heat treatment in industry, you might find T6, T5, T4, etc. They will mention by letters particular heat treatment operations they are carrying out for aluminum, and these refer to particular profiles by which you will do the tempering operation. So T6, for example, will give you temperature versus time curve, and it will have a specific curve like this. Maybe you have this and then go to 0, something like this, a curve like this. T4 will have another curve like that. So there are specifications given. What should be the temperature, what time, in what time I should increase the temperature to that particular temperature, etc. All these details will be given by this designation according to standards. And if you do these particular heat treatment processes, and you will find that the yield strength of the material changes. Let's check aluminum. Tempering, maybe I use T6, maybe they give a curve. So you can see here 6061 aluminum alloy, T6 tempering heat treatment process. So this is how you have temperature. On the x-axis you have time, and it gives you exactly how to do the heat treatment. 3 to 5 minutes. You increase the temperature from room temperature all the way, you go to 535 degrees centigrade. You maintain the temperature for 35 minutes inside the oven, and then you drop the temperature suddenly back to room temperature. Okay, you quench, you do a quenching operation, put it in an oil bath or maybe in cold water, and then bring it to room temperature, and then again in 2 to 3 minutes you again increase the temperature and do tempering operation. Here at 190 degrees centigrade, then you air cool. So here you are given water quenching, and here it is air cooling over a period of 60 minutes. So if you do this operation, it will give you certain desired output of the materials. Okay. I think it won't allow me to change. Okay. All right. So again, we are towards the final part of the chapter. Here we'll briefly go through different categories of materials. You have metals and alloys. You have ferrous alloys and non-ferrous alloys. You have aluminum, copper, different types of alloys here mentioned. Among ceramics, you have list of the materials. Again, here you can see concrete, brick, etc. They are listed. Tungsten carbide, silicon nitride, silicon carbide, boron carbide. All these are used in tools. Aluminum nitride as a coating as well. Alumina is used as a ceramic material, as an insulator, and you can see again different materials. Even stone, naturally occurring stones, they are ceramics. Glasses are again classified as ceramics, but these are ceramics with transparent or translucent properties. Polymers we have seen, thermosets and thermoplastics and elastomers. Some examples are there. Again, you can see here. See, elastomers separately given, naturally occurring rubber or artificially made rubber materials. Hybrids are composites, foams, and other natural materials like wood, bamboo. All these naturally occurring materials are also hybrid materials. Okay. Okay. Finally, we go for Ashby's charts. What are Ashby's charts? Ashby's charts will be used extensively to select materials. Okay. So in this example, what we see here is Young's modulus. According to Young's modulus of the material, we have different classification of the material given here. A distribution of materials. You have tungsten carbides with the highest Young's modulus values reaching almost 1 terapascal, 10 power 12. Okay, and then we have other materials. Remember, this is on logarithmic scale. Okay, this is on logarithmic scale, and we have alloy steels, probably 200, 300, 500 megapascal, and reaching a gigapascal value, and other materials listed. On the lower end, we have polymers. Somewhere in between, you have hybrid materials, metals, alloys, ceramics at the top. We can also have a comparison of Young's modulus and density of the material. Often we want to have very high strength material with a low density. So we need a comparison, for example, between Young's modulus and density, yield strength and density as well. Something like these plots. These are also Ashby's charts. And in this particular chart, you can see a simple example here. You have foams, different types of foam materials are here, right here, where foams are materials what you use in your pillows. For example, cushion materials. These are all foams because it consists of voids, air pockets, and some soft material. Obviously, it will have very low Young's modulus value and very low density. So therefore, all the foams are listed here. You have elastomers right here, very low Young's modulus, but density may be slightly higher than the foams. You have polymers over here, and then some naturally occurring hybrid materials also here. Then we have metals and alloys, ceramics within this grouping, then composites somewhere here, and then concrete here, along with composites. So these are various bubbles, and usually you will find that Ashby's charts will contain materials distributed on a chart like this and represented with the bubbles like these. Along with this, you will have what are called as material index guidelines. So here you have E versus rho, square root of E versus rho, cube root of E versus rho. So why do we have these lines? Depending upon the type of load you apply, you can derive what is called as the material index for your problem. And when you derive the material index, depending upon the type of load you have, for example, for axial load, you will have E over rho. And maybe for a different case, let's say take for a beam bending load, you may have square root of E over rho as the material index. And you want to make a selection of the material based upon these material indices. Once you obtain, let's say, material index E over rho, then you will draw these lines. Now E over rho will have a certain unit, and the unit, if you calculate, it will become meter per second. And these E over rho values on this graph can have, these lines can have different values, 10 power 2 here, 10 power 3, 10 power 4 here, etc. Depending upon these values, you can choose the material. For example, if I want very high E over rho value, the lower value is towards this end, the higher value is towards this end. So I will have to choose materials in this direction, going in this direction. The higher the E over rho value I want, the higher the value of the line here that I have to choose. Okay, so for example, I can specify my E over rho value here somewhere in between 10 power 3 and 10 power 4, and I can choose this particular line here. Or any material which is chosen above this line will satisfy the criteria. So I can choose wood here, or any ceramic material, or any metals and alloys above this line given in this bubble. That will be a suitable choice for us. Sometimes, along with the material index, I want to choose a minimum value of Young's modulus. For example, I want something with a E value greater than this. So I can combine both these lines in this case and choose material above this blue marked line. I can also choose materials by drawing a box around it. Okay, so specifically inside the box, and then based upon my condition, I can select this material. So this is how, in short, we will use the Ashby's chart. We still have to see how to derive these material indices. And in your exams, you will definitely get a problem on material selection. So let's see more examples here. So one example is given here, specific modulus ratio of Young's modulus to density. This is selected as one of the material index. Specific stiffness can also be selected. Useful to minimize weight with the primary design limitation of deflection, stiffness, or natural frequency. Okay. So when you choose high E over rho values, what happens? It gives you an idea how to on how to limit the deflection in a certain member. For example, if you have a shaft, you want the limit. If you want to limit the deflection of the shaft, maybe you will choose E over rho, or specifically square root of E over rho, high values of these particular ratios. That will limit deflection. Similarly, stiffness. So instead of having the property E, I can also have the stiffness Sy over rho. Okay, that is it. So this will be specific strength, not specific stiffness. I can also have specific strength if I want high strength. Okay, just like specific stiffness, this one, I can have specific strength as well. So let's see here. We have one example, e power beta over rho. Beta is can be taken equal to 1 for axial loading case, and beta equal to 1 over 2 for bending case. So let's see how to derive E over rho ratio for the axial loading case. Please pay attention. This is very important, and in your exams, you will get problems here. Okay. So let's take the axial loading case. P is the load, A is the area of cross section. And for this particular case, I want to minimize any elongation. Okay, so what is the objective? So when we derive material parameters, material index parameters, first we need to identify the objective. Okay, so what is the objective going to be is, in this particular case, since I want, let's write the question as light stiff bar is the question. I want you to get the material index for a light stiff bar. Okay, so what is the objective function? Since it is light material, minimize mass. So that is going to be your objective or goal here. Then you want to identify what are called as free variables. What are free variables? Usually in your problem, I will give you some data, geometric data. For example, the length of the bar is fixed, okay, and you are free to choose. I might say you are free to choose area. Free, yeah. Okay, so then what happens? Your free variables, they become area of cross section, shape of the cross section. I didn't specify what should be the shape. Okay, shape of the cross section, that is a free variable. You can choose whatever you want, and fixed variables are usually the load you have, L you have, the property L, etc. Okay. Okay, so based on this, I want to derive what is the material index. So since the objective function is to minimize the mass, okay, and I want to choose the material in such a way that the bar is stiff, I write the equation for mass. How do I get mass? Rho density, mass density of the material, multiplied by volume. Rho multiplied by volume, volume can be written in terms of area free variable times the fixed variable L. I cannot do anything with L, but I can do something with the rho, something with A. Okay, so now how do I change? And I need to minimize this. Remember, minimize mass. Okay, so here I want a stiff bar. Okay, so what do I do? So if you go back here, let us see. Let's try to derive here a formula for stiffness. So since I'm interested in stiffness, I'm going to write the formula for stiffness. Okay, what is stiffness? It's similar to the spring stiffness. Is usually defined as F over delta. Okay, if you replace the bar with a spring with a force F, K, we can get this relationship. F is equal to K times elongation you have here, whatever elongation you have here, delta. So K can be written as F over delta. So let us say my stiffness is some S star. Okay. Okay. So based upon this, let's see here how it is derived. Okay. Okay. Now, how do we get what is the stiffness here? We compare. We can take the force F of a spring and write it as K times delta. Similarly, we can try to come up with an equation for a bar. Okay, so how do I obtain an equation for the bar? From the Hooke's law, I can write it as E times string. So this is Hooke's law. I'm going to replace my sigma with the internal force F over area of cross section is equal to E times strain. I'm going to write it as by the replacing with the formula delta over original length. Let's call since we have the original length L. So I'm going to write it as L. I'm going to rewrite the same formula in the form f is equal to k times delta. Okay, and let's write it here. F is equal to E times E over L times delta. So this gives me what is K. Okay, so implies my stiffness in this case is E times A over L, and I'm going to take it, this guy should be equal to S star, the stiffness value S star, whatever value I am taken, I want. Okay, so based on this, I can come up with an expression for A, stiffness times L over E. I take this expression now, substitute inside the mass term here, rho times A times L. A, substitute, here. Now what I do is I'm going to group it into geometric properties, physical the material properties, and the physical properties like stiffness. So if I rewrite this mass, I can separate the stiffness property separately. I can write it. Then I have the geometric property. What is the geometric property? L square. Then I can bring in the material properties rho and E together. Okay, so by doing this, I can figure out when the mass M can be minimum. Now, usually the stiffness here, okay, by design, I would have a certain limitation on how much the bar can expand. So my stiffness property is usually limited. It's not a free variable. Okay. So these two guys, they are not free variables. Not free variables. I cannot do anything with respect to these two guys to minimize the mass, but I can play with the other term rho over E. So I take my material index as inverse of this guy. Usually we take the inverse of this guy as the material index and write this as the material index. And material index will be usually material properties. Okay, so this is how for the axial loading case I get the material index. Now what is my specific objective? I want to minimize mass. How do I minimize mass? By minimizing rho over E. So this guy I have to minimize. I choose my material in such a way that this ratio is minimum. In other words, the inverse of this should be maximized. So this guy must be maximized. I choose my material such that my material index is maximized. Okay, so this is just one example. I think the time is almost up. I will go through other examples on how to derive material indices in other cases. For example, with respect to strength and axial loading, we will see exactly how to derive the material index for strength. Okay, and we will also see how to get material indices for other types of load. Okay, any questions up till now? Okay, so if you don't have any question, next class I will also go through the software. Unfortunately, I already told you the software is not available for free, but I will show you the software which can give you this particular ASHBase charts. And by just drawing a box around certain areas and specifying the material index, you will be able to select different materials for your application. Okay, so if you don't have any other doubt, I'm going to stop right here and we will continue again from Sunday 8 o'clock. So see you guys and I'll meet you on Sunday.